Data published in the August 2018 issue of Antarctic Science reveals an 88.3% demographic collapse of the Morne-du-Tamaris king penguin colony. In 1982, this colony reached a peak population of 500,000 breeding pairs. Representing roughly 2 million birds, it was the largest king penguin colony on Earth. By 2018, high-resolution orbital surveys discovered the population had plummeted to approximately 59,200 pairs. The collapse occurred on Île aux Cochons, a 67-square-kilometer volcanic dome in the southern Indian Ocean. To protect the delicate ecosystem, the French Southern and Antarctic Lands Authority maintains strict biological isolation. Human foot traffic is almost entirely prohibited. Because of these access restrictions, nearly 90% of this apex predator population vanished over 2 decades without a single human observer recording the event.
This unobserved eradication establishes Île aux Cochons as a critical sentinel event, a case study in how quickly ecosystems crash when biophysical thresholds are crossed. Auditing a biosphere reserve where human presence is banned requires a multi-spectral satellite record to reconstruct the timeline of the loss. This is the baseline guano spectral reflectance captured by Spot 2 and Spot 4 satellites in 1998, showing the original extent of the nesting grounds. By 2006, the Spot 5 satellite recorded a subtle contraction along the perimeter of the core nesting area. Because on-the-ground verification is prohibited, this shrinkage went unremarked. But 2016 satellite imagery confirmed the footprint collapsed to less than 15% of its 1980s density, with secondary vegetation encroaching on former nesting sites. Early theories suggested the missing 440,000 pairs hadn't died, but had simply moved to a different island. This prompted an orbital search for population spikes on other sub-Antarctic landmasses, such as Kerguelen or Marion Island. Regional satellite telemetry across the entire Southern Ocean confirmed no such displacement had occurred. There were no new colonies and no expanded populations elsewhere. The demographic drop was a 100% net mortality event. This mortality proves the failure was not a behavioral shift, but a systemic environmental collapse isolated specifically to the Morne-du-Tamaris colony. The root of this failure traces back to 1997, during a peak El Niño Southern Oscillation event. This coincided with a massive positive Indian Ocean dipole, creating a severe compounding disruption of the entire regional oceanography. This mapping of the southern Indian Ocean shows the intense heat anomalies recorded during this period. These temperature spikes forced the nutrient-rich Antarctic polar front hundreds of kilometers southward, away from the islands. King penguins depend on a highly specific foraging strategy, hunting myctaphid fish found at the edges of this front. They dive between 100 and 300 meters, utilizing the thermocline and winter water layer to find prey. When the 1997 front displaced, those prey patches shifted deeper into the circumpolar deep water and moved significantly further south. The biophysical limit for an adult king penguin foraging from a breeding colony is 722 kilometers. The southward retreat of the polar front pushed the optimal foraging zone definitively beyond that 722-kilometer threshold. This created a thermodynamic failure. Parents expended more energy reaching food than the food provided, leading to a rapid decline in body condition. This energetic imbalance resulted in widespread chick starvation, as adults were unable to return to the island in time to provision their young. Exceeding this energetic limit left the massive population severely immunocompromised at the exact moment their density was at its historic peak. This starvation-induced weakness was compounded by secondary stressors building within the food web. Ecotoxicological assessments of feathers from the archipelago show a heavy mercury concentration of 1.98 micrograms per gram of dry mass. As these heavy metals biomagnify up the marine food web, they cause chronic physiological impairment in top predators like the king penguin. This chemical burden interacted with the widespread presence of pathogens. Results from regional bird populations showed 62.6% of samples tested positive for at least one infectious agent, including the highly virulent bacteria that causes avian cholera. While climate forced the initial decline, this high disease prevalence points to an unrecorded epizootic event as a plausible candidate for the massive mortality spike. In an immunocompromised and extremely dense colony, A virulent pathogen could sweep through 500,000 pairs in a matter of weeks, leaving no physical evidence behind. Another possibility involves the island's volcanic nature. Unmonitored subsurface geothermal degassing, like sulfur dioxide, could have caused acute asphyxiation in the low-lying nesting valleys. The collapse reflects a synergistic tipping point, a moment where climatic displacement triggered widespread starvation, which enabled a massive disease outbreak, or left the flock vulnerable to geological events. The anomaly at Crozet is a preview of the systemic changes projected under IPCC emission models. By mapping these divergent scenarios, researchers calculate how the absolute limit for penguin foraging will shift. A 1.5-degree warming is predicted to displace the Antarctic polar front up to 4 degrees southward, a total poleward shift of 400 kilometers at roughly 40 kilometers per decade. Under the RCP 8.5 scenario, 70% of the 1.6 million king penguin breeding pairs are expected to abruptly relocate or disappear before the century ends. The assumption that these birds will simply move further south to islands like Bouvet or South Sandwich is likely incorrect. King penguins require a 14-month ice-free cycle to rear their chicks. The severe sea ice coverage on these extreme southern islands makes successful breeding there biologically impossible. The fact that 90% of the world's largest colony vanished without being seen highlights the primary vulnerability of remote biosphere reserves. Protecting these populations requires a shift toward tools that can monitor the health of a colony without requiring a physical human presence. Non-invasive eDNA sampling of runoff water and AI-driven guano reflectance algorithms are the only means of detecting these mortality cascades before they annihilate the remaining apex populations.